Alright, part 2 is going to be the theoretical about how I got everything working LED wise. If you want to skip to the next video for more brute force hammer and painting fun, then be my guest. Otherwise, settle in for some learning. Yeah, retrograding for several days in the sun didn't do anything. I also tried to sand the corner down. These are just sun bleached. This one particularly is. Nothing I can do there. Before I put anything back together, I just wanted to show what I did here with the LEDs and the resistors there. So these basically replace the bulbs. The reason for doing that was because this bulb here is what was needed for the stoplight, and it's a 52 volt light. I looked online, they were like $15, so it was much cheaper to go into my parts bin and get this. This is a taillight assembly out of a Hyundai Ecoped. They don't exist here for this year model because this came out of a Korean junkyard when I lived there. And it's come in handy for several projects. So it was cheaper for me to cut that out to fit in here. I had to notch it here and there. It's screwed in. They're screwed in here as well. And then right there's one too. And these are automotive grade bulbs, I guess. And it was cheaper for me to buy 10 of these off eBay, these resistors, and wire them into the light assembly there. So in order for me to figure out what was going on with the situation with the LEDs, how much voltage I need to drop. So first I'm going to have a look at how the manufacturer did it in that strip of LEDs I showed you. So that is your standard LED. Those ones were a bit bigger. But from what I've read on the internet, these LEDs, red ones, usually take about 1.7, I'll use a marker. They use 1.7 volts, and they draw 20 milliamps. So, I mean, that's just an assumption based on some of my findings. So what you need to get an LED going is a power source and an LED. Chances are you're not going to have a power source that's directly connected to the LED. It almost never happens. You will need a resistor. So this is pretty straightforward setup. It's in the same thing in the car. So electrically, on a schematic, it would look something like this. You have your power coming in, and that is the symbol for the LED. And I'm going to ground it. And here, there's a beautifully drawn resistor. And then there is plus 12. We'll say plus 14. The reason for that being is when the car is on and the alternator is charging the car, I actually get about 14.5, 14.7 depending on the state of the discharge. So we'll just say 14. So, I mean, with these values, we can use V equals IR to get what we need. However, I already know the value of this resistor to be about 620, I believe, from the color codes on it. But it's worthwhile to go through this exercise to figure out how the manufacturer got this, assuming these values. I mean, they could be a little bit more, it could be a little bit less, but based on this and this, which I know for sure, we can calculate that. So the way to do that is I'm running out of space here. Okay, we'll do it that way. So, the resistance is the source voltage minus the forwarding voltage, which is how much this is, the voltage drop across the LED, divided by the current drop of the LED. So we can calculate that out to be 14 minus 1.7 is 12.3, and that is 20 milliamps, which is 0.02 amps, leaving you with 615 ohms. Okay, so that's how they got that. So the manufacturer of the e-bike, as well as most cars produced before, I don't know, 2010, whichever ones used incandescent bulbs. In a car, the old system is 1157 is a dual filament bulb, and 1156 is a single filament bulb. What that means is you have one bulb either way, so that's your automotive light bulb. Normally you have one prong at the bottom, and it's simple negative positive connection through, a filament and that filament lights up and you get energy. So in an 1157 you have two filaments inside one bulb, and there's two prongs at the bottom. When you turn this in to a socket, it connects two different circuits. So the same idea here, except the e-bike has a 52 volt bulb. Yay, fun, proprietary. So how this works is exactly the same way. Both of the ends of the filaments are one end are grounded, so the metal chassis is ground, and these two are connected to the bottom prongs internally. So you have two different filaments in here of different resistances. In a car, the brighter brake light is, I believe, 21 watts, and the running lights are 7 or 8 watts. So 3 times dimmer, I suppose. So it is one bulb, but there are two separate circuits inside here. And that's good and well because they're very isolated. I mean, they have a common ground, but that's it. So the bike or the car would have a brake light. You stomp on your brake, you get, bam, this one lights up. And if you have your parking lights on at the same time, the brightness of the 21 watt filament overpowers the 7 watt one, and this one's still on but you can't see it. So two separate circuits. So how do you connect those two circuits into an LED system? Basically, you'll be using an LED, a few resistors. I used 3, and we'll go into that in a minute. A power source, and a diode of non-light emitting type. So here's how that works. Basically, you still have the same setup of the LED. And it's grounded here. There's the resistor in there. Okay, that's your 600 ohm resistor. So basically what we're doing here is we're taking straight out of the car setup, the 12 volt setup, into the 52 volt setup. And here's how we're doing that. Alright, so we'll call this valueless for now. We'll call them R1s. So this is how this particular setup works. It will work. Actually, is working. It works just fine. So this is your brake circuit, which on the other end is activated simply by, I can continue this actually, just a normally open switch. And that goes to your plus 52 volts. This is your ground, so it essentially creates a loop. This one is a little bit more complicated because it runs into other parking lights on the front of the e-bike. So what I've done here to isolate the circuits is to put a diode in. So this we'll get to calculating the resistance of that in a second. Functions in one simple loop. So plus 52 volts goes into this resistor, which drops the appropriate voltage down to about 12 volts, which then this one drops it down to the 1.7 the LED needs, and it turns on. When you hit the brake, that switch closes. So when you turn the running lights on, what you're going to do is you're going to go through two resistors, because you want the light to be half as bright. And same values are used here, and the only difference is here it goes through this diode. Basically the current will only flow in one direction. So when your running lights are on, you get this circuit going here. And also, yes, the current is going in through here too, but it's stopped at the switch, so it doesn't really matter. If this was connected to other things like sensors or a readout of some sort, like if this was part of an IC, right, you wouldn't want power going through it when the running lights are on. So you would just put literally another diode there. I didn't need to do it in this case, but that would be the proper way. So going in through here, coming out through there, and when this one's on and you hit the brakes, your current's going through here and going through the LED as well, but it's getting stopped here. Now if you omit this, what will happen is the current will keep flowing through these resistors and light up whatever is attached to the circuit. I know for a fact in the e-bike it has front light running lights, so they would turn on, albeit dimmer because of these resistors, but they would still turn on, and that would just be weird. So that's how I solve that problem here. So how did I get the resistance values to bring it down from 52 volts to 14. Really easy. I just used the same formula. So we know the input voltage is 52. We know the voltage drop will be 14 across the black box circuit, because basically what I've done here is just taken the old circuit from here and just black boxed it. And the resistance are the amps don't change. So you're basically going to be left with 38 divided by 0.02, and your resistance is 1900 ohms, 1.9 kilo ohms. I bought 2.2s. I did calculations a bit earlier. I don't know where those calculations are to be found now. So, but they're very compatible, and this this situation works. So, on top of that, to dim the lights, I just literally trial and error, put 2 of them in line, and I was happy with the outcome. I'm sure there's a calculation for that somewhere. If there are any electrical engineers looking at this right now who want to correct me, put them in the comments. And a final note, why would I go through all this effort? Why not just get the $15 bulb? You know, it's not because I'm cheap, although, I mean, yeah, but it would just be easier to do it that way. The other thing is, one of the turning signal bulbs was also burnt out, and I just had these LEDs lying around. I had a bunch of diodes. I had everything but the resistors. These are not the resistors that I got, but they're very similar. So I bought 2-watt resistors. The calculation power draw, believe it was calling for 1.1 in the calculations. Those kind of resistors don't exist, so I just went out ahead and bought 2-watt resistors for the low price of, I think it was $1.59 shipped to my door. So I mean, really, to have a little bit of fun and have LEDs which never burn out, it's cheaper to run, and you know, keeps the old noggin working, because if you don't use these this math, you know, you're gonna lose it.